So, we will continue our discussion on the non-classical MOSFETs, which I explained what it is in my last lecture. Okay. So, this is module 1 continuing on the carrier transport in nano MOSFET. So, we discussed last time, just this is a repetition of what I said last time, because I am continuing on that. Okay. So, the subthreshold region has an exponential characteristics, which already you have heard number of times, and on the log scale it will be linear. And we also saw that subthreshold slope or subthreshold swing is 60 millivolts into n. 60 millivolts is kT by q ln 10. And we also saw that this n is nothing but an indication of how good is the coupling of the gate with respect to the channel. If delta VGS is exactly equal to delta psi of s, the coupling is excellent. But because of the sharing of the voltage between the gate oxide and the depletion layer, the coupling is not that good. So, what you get will be VGS will be shared between these two, and we also wrote, since psi s is less than VGS, we wrote VGS by n is equal to psi of s. So, then delta VGS by delta psi of s will be n. So, that n is actually the coupling factor, ratio of these two psi of s and VGS. Okay. And from these two capacitances, you can see that the voltage or any change in the gate voltage will result in a change in psi of s decided by the capacitance ratios, and that is delta psi of s is equal to delta VGS divided by sum of the two capacitors multiplied by C oxide. That is a standard basic relationship. So, from here delta VGS by delta psi of s is 1 plus C d by C oxide, where C d is the depletion layer capacitance per centimeter square. I call it centimeter square, but per unit area, and C oxide is oxide capacitance per unit area. So, you can see that if the depletion layer width is smaller, C d will be larger and then n will become larger. Okay, that one indication of this subthreshold slope will be much more, that is, you want n as small as possible, ideally 1, you will never get 1, but you will see you can have some special structures where the n can be brought very, very close to 1, 1.01 like that of that order. Okay. Now, we want to see is this is the ideal situation where there are no, the surface is excellent, but in practice you have got interface states, interface state density is there between the oxide and silicon, particularly if you are talking of high K dielectric, it will be unbearable. So, you have to see what will be the effect of that. So, just before going to that, I thought I will give a quick glance of what is implied by this surface state density and how it arises. I know that Professor Naukan Bhatt has already discussed some aspects of this, maybe some other things which I would like to elucidate, I will just quickly go through. So, if you take a semiconductor, energy band diagram has no states in this between the conduction band and valence band, that is a forbidden band. Now, any loss of periodicity or presence of any impurity will give rise to levels between the conduction band and valence band. So, to give a very good example of that, donors. Donor is a fifth group element which has one valence electron, which I have shown here, and the core is plus charge. And this one valence electron is the fifth electron of the fifth group, which will be revolving around that, which is very loosely bound. So, you can give, even if you give very, very small energy, even at room temperature, this electron can be raised, removed away from this parent atom, and it can go to the conduction band. So, when you put the energy level here corresponding to the donor level, a shallow level, implication is you can raise the electrons from this donor level to the conduction band with very small energy, some 50 milli electron volts. for that is called shallow donor. Okay, that is why I put it near the conduction band. I have a why I am going through this is because we want to see what happens in interface state density. If you take acceptor, see here the donor, the core is plus, if you remove the electrons from there, it is positively charged. Acceptor, the core is negative, there is a site where plus charges you can look into as the vacancy, you can assume that there is a plus charge. So, that whole thing as it is neutral. So, if this plus charge is removed from there, that is how can it be removed? By accepting electrons from the valence band, that plus charge is neutralized. So, you will get negative charge. So, here you donate electrons, here you donate plus charge, and you donate the plus charge by taking electrons from the valence band. So, when it accepts an electron, this is plus charge is gone, it is negative charge. So, that is what to put it once more, if the electron is occupying the donor level, it is neutral. If the electron is occupying the acceptor level, it is negatively charged, because the plus charge is not there. Okay? That is the thing to understand the interface state density and its impact. Now, let us see what is the. So, these are the shallow donor and shallow acceptor, implying very small energies are required for interaction between the donor level and conduction band and the acceptor level and the valence band. Now, if you take a surface, I take this surface, this is the bulk, this is on the surface. If I take the atoms are the surface of semiconductor, atom does not have neighboring atoms. Usually, in the bulk of the silicon, the atom is surrounded by 4 neighboring atoms. So, all the bonds are continuous, it is stably staying there. The atom on the surface has got 2 on the side, 2 on below. It is a very qualitative description, but there is no atom on the top surface. So, above the surface there are no atoms. So, there is an electron which is not forming the bond completely. So, there is a possibility that you can knock out that electron and take it into the semiconductor, make it available for a conduction if possible. Okay. So, that means that silicon atom on the surface can act as a donor if it donates an electron. Now, where will locate its energy level is the question. See, the shallow donor, the electrons can be knocked out with very small energy. So, you locate it very close to conduction band. Now, let me ask you, if you knock out electrons from the valence band, that is the electrons from the bond, you have to apply a energy equal to 1.1 electron volts. That is why the conduction band valence band difference. But if the silicon which is on the surface, from there if you want to knock out electrons, you may not require as much energy as this required for the electron band gap, but it will not be as small as what you require for this pentavalent material. So, it is actually this level corresponding to this donor will be very close to valence band. It is not near the conduction band, implying it will require large energy, much more large energy than the shallow donors. They are called deep donors, which are far away from the conduction band. Similarly, you can argue that for the valencer, the acceptor type deep levels can be on the upper band from the same argument. So, why I am bringing out donor and acceptor is the surface atom can either donate an electron or it can take an electron to complete another bond. So, it can act as a donor or acceptor. If it is acting as a donor, that donor level can be located near close to valence band, somewhere in between the mid gap and the valence band. The acceptor level on the same argument will be on the upper half of the band gap or closer to conduction band. Now, one more thing that I want to point out is there are about 10 to the power of 14 to 10 to the power of 15 atoms per centimeter square on silicon. That means large number of atoms are there. Now, let us go back to the shallow donor or shallow acceptor theory. If there is shallow donor, you do not put that donor level as continuous level, you put it by dotted lines. What is the implication of that? The implication is very simple, it is very dilute in silicon. the number of atoms per centimeter cubed in silicon atoms are about 5 times 10 to the power 22. Now, the donors which are there in dopants, when you dope them, are 10 to the power 18, 19, 20. About if it is 10 to the power 16, 17, etc., it is very, very dilute. Out of 10 to 22 atoms of silicon, there are 10 to the power 16 or 17. So, these two atoms do not see each other. See, a conduction band was a band of levels. Why? It was interaction of the energy levels of the silicon atom. How the interaction comes up? The spacing between the atoms is very, very small, from 5 angstroms. So, that is why from Pauli's exclusion principle, you can say that no two energy levels can be at the same level, okay? Corresponding to that. So, it splits up. Similarly, if the donor level, now you put it dotted line saying that it is not interacting with each other, they are isolated from each other. Now, if you raise the donor levels, donor concentration to about 10 to the power 20, 10 to the power 18, 19, 20 and all that, then number of atoms are very large and number of distance between the atoms, donor atoms is reduced. There can be interaction between the wave function of these two atoms. That means, the two electrons trying to occupy the same energy level, but they are not able to occupy the same energy level, they split up. So, this donor level, which you put it as a donor level 1 level, with no longer will be 1 level, it will split up into a band of energy. It will split up band of energy and it can even merge with the conduction band. Similarly, the p acceptor levels also can split up into a band. So, now going back to this theory of surface states, you would have seen already. Now, I have argued out that if it is one atom, there will be one acceptor level and one donor level. It can go either way, it is amphoteric. For example, if you put gold into silicon, it has one single electron, valence electron. It can either donate or accept. Okay. So, in the same way, surface states, electrons can go and occupy, or it can donate that electron that is available there. So, now that is one atom has got one acceptor, one level and one donor level, and we said donor level will be below and acceptor level will be up, because of we argued it out. Here donor level is up, acceptor level is below. There deep levels will have donor levels down, acceptor level is up. Now, if there are large number of the surface atoms like this, each of those donor levels will split up into a band. See, donor levels are below. Each of those acceptor states is split up into a band. Okay. So, that is why you put these acceptor states closer to on the upper half or nearer the or above, and donor levels below, and all of them are not one levels, several levels split up, a band of energy levels, because large number of surface atoms are present. Each one of those surface atoms corresponds to one level here, one level here. Okay. Now, other thing that you have to see here is these acceptor levels will be actually occupying from top to bottom completely, spread out. But when you come down here, there are a large number of donor atoms which are compensating that. So, you can say that predominantly there are acceptor levels up to a point, predominantly there are donor levels in this region. Between the level called E naught and E b, they are all donors. Between level E naught and E c, they are all acceptors. I hope that is understood. Now, this argument whatever I have discussed I have put here. What is the charge state of these? See, I am not showing the intentionally doped shallow donors and the shallow acceptors. This particular material, if I put the Fermi level here, what does it mean? It is a p type material, and I have taken the doping such that the Fermi level actually coincides with the E naught level, which separates the acceptor level and the donor levels. So, this E naught level is called the neutral level. Why it is called neutral level? In this particular case which I have shown, the Fermi level is coinciding with the neutral level, with the level E naught. Okay. What is the meaning of that? What is the charge state of these acceptors? From the definition of Fermi level, if you recall, all the levels below the Fermi level are mostly occupied. The levels above that are not occupied mostly. In fact, if you go to the 0 degree Kelvin, all the levels below the Fermi level are occupied, all the levels are empty. But at room temperature, if you go, slightly deviation will be there, but for qualitative understanding, you can say almost all the levels are occupied below, all the levels are not occupied. So, if you take that abrupt model for the Fermi Dirac distribution, these are all not occupied. Now, go back to what I mentioned. All the donor levels are occupied because they are below the Fermi level. So, what is the charge state of that? Just go to this and see, they are occupied, means it is neutral. So, these levels are neutral because they are all occupied, and the acceptor levels are not occupied by electrons, which means that is neutral. If it is occupied, it is negatively charged. Okay. So, in this case, you call this as neutral level, because if the Fermi level is coinciding with that level, the levels below that, which are donors, are occupied, so it is neutral. Levels above that, E naught, which are acceptors, are not occupied, so they are neutral. So, charge, net charge on the surface is 0. So, energy band diagrams will be flat. Now, let us go further down. I am going a bit slow because this is very, though you had gone through some of the things quickly, I will see go through that. Now, I will take a situation where, see here it was a situation where it was a p type, Fermi level doping adjusted, bulk doping adjusted, such that Fermi level is coinciding with the E naught. Now, I go to a n type material, doping is something like 10 to the 15 or 16, Fermi level is close to the conduction band, decided by the shallow donors. Now, surface is free, there are no oxides, there are very large density of states. So, if it is like this, if I draw the energy band diagram like this now, all the levels below EF are occupied. What will be the charge state of this? Take a look at these levels below E naught. They are donors, they are occupied. So, the charge there is 0. Okay. Donors charge is occupied. If it is donated, it is plus charge. It has not donated, electron is occupying, it is neutral. And these are acceptors, electron is occupying. That means electrons, it has accepted electrons. That means it is negatively charged. So, on the surface of the semiconductor, there will be net negative charge. Donors are donating, acceptors are accepted. Where has this electron come from? That has come from semiconductor. That means this n type silicon removed some of these electrons from the nearby region from surface and given it to these acceptors donated, which means the surface, the region near the surface will be depleted of donors. See, these are the donors plus charges, this is a depletion layer. The electrons from here have gone to this surface. Surface is negatively charged and there are donors which are positively charged. So, once there is a depletion layer like this, electric field is in that direction. So, what happens to the energy band diagram? I hope you are familiar about the energy band diagram. So, electric field is in this direction, that means the band bending takes place. See, if there is no electric field, energy band diagram is flat. Wherever there is a depletion layer, there is an electric field and the energy band diagram will bend like this. So, up to this point, there will be band bending, and since electric field is in this direction, energy band diagram will bend upwards like that. How do you figure out that? When the electric field is like this, you have to spend energy to take electrons from here to here. So, if the electron is here, it is at a higher energy level. That is why energy band diagrams bend here, that is why it runs like this. Now, that is some important thing that you have to understand here before we go next into the argument on some of these things is what happens. See, because of this band diagram, because of the electric field, there is a potential drop from here to here. That means, this is neutral, surface there is a potential equal to psi of s. From here to here, if you go, there is a potential which is negative with respect to this point, that is psi of s, that is surface potential. Potential of surface with respect to neutral region, and that potential is actually equal to the voltage drop across the depletion layer, which you know is on the first order theory q n d w d squared by pi epsilon epsilon 0. That is a well known thing. Okay. Now, charge in this region is Nd is number per centimeter cube. I am computing charge per centimeter square. So, per centimeter cubed, if it is Nd cubed, multiplied by Wd, I get total number of charges per centimeter square into cube. Now, what will be the charge on the surface now? That will come back after discussing one particular point here. I mentioned that the energy band diagram will bend. What will be the state of affairs for the Fermi level? Fermi level here was decided by the donor's concentration in the bulk. Okay. So, in this region where it is neutral, the energy between the conduction band and the Fermi level remains the same as before. It does not change. But as you move to the surface, because it is depleted, it becomes less n type. Electrons have been donated. That means, the Fermi level will be farther away from this point. 2 points here, the Fermi level is decided by the doping concentration. Here, the Fermi level difference between the conduction band and Fermi level depends upon how much band bending has taken place. It is less n type here. You can think about that. Less n type means Fermi level distance between these two will be larger. Other point that you must note is the Fermi level is horizontal, it is not bending. If you recall some of the discussions or earlier models, the Fermi level will be continuous. There will not be any deflection or deformation in the Fermi level if there is no current flow. It is a thermal equilibrium situation, there is no current flow. So, that is why F is constant. Okay. So, all that happens is band bending takes place upwards, this remains constant. What happens to neutral level? See, if you go back to this, the neutral level is assigned, is fixed for a given material. If you take silicon, the neutral level is 1/3 of the band gap here. If this is the band gap energy Eg, this is Eg by 3. It depends upon the particular material. If you take silicon, it is about Eg by 3, that is E naught minus Ef. If you take gallium arsenide, it is also almost that. If you take germanium, it is very, very close to valence band. In fact, 0.66 electron volt is the energy band gap of germanium, and E naught minus Eb will be 0.06 electron volts, very close to valence band. Depends upon the material. Let me not get into the details of that, we will be lost in that otherwise. Okay. So, the location of E naught with respect to Ev is fixed, Ev or Ec is fixed. So, if there is band bending taking place like that, on the band bending has taken place here, Fermi level has the gap has changed from here, but the location of E naught with respect to valence band is same on the surface, which would mean, see, if it was like this here, because of the charge transfer from the semiconductor to the interface, the Fermi level has, this has moved up. So, the distance between the Fermi level and the E naught has reduced on the surface. So, the band bending is such that charge here is equal to the depletion layer charge. Okay. So, all this discussion is to go into what happens further. This is n type. Please remember, it always moves closer to the neutral level, so that the charge here is equal to the charge in semiconductor. See the other case of p type, where if the Fermi level is below the E naught, what would happen? These are in neutral level is above the Fermi level. Now, the levels below the neutral level are donors. That means, these donor levels, what happens to these donor levels? Above the Fermi level, here they are Fermi level. So, you can see donor levels between E naught and Ef are not occupied, levels above Ef are not occupied. So, these donor levels would have donated electrons to this p type material. So, p type region, if it is made negative, it will be depleted. Plus charges, see, donor electrons have gone and neutralized the p type plus charges. So, there will be depleted layer. In the previous case, n type has depleted, its p type has depleted. Okay. So, you have a depletion layer. Once it is depleted, because it has donated electrons, surface is positive and this is negative, electric field is in this direction. You can see band diagram is up like that to the right, because field is in that direction. Okay. So, ultimately you can see that the band bending takes place and the voltage drop in the depletion layer is such that net charge in the surface that is equal to net charge in the depletion layer. This I will give one more instance which I will not discuss. This you at your leisure time you think of that, what will happen. This is not equilibrium situation. If there were surface states were not there, I have a situation where Fermi level is above the E naught. Okay. That means, these are the acceptor states which are occupied there. What way the energy band diagram will bend, what will happen to the semiconductor surface, that I think I let you to discuss when you go back. Okay. In fact, what you have to realize is the levels below the Fermi level are occupied, that means these acceptor levels are occupied. Okay. That means it has taken electrons from the semiconductor, that means it has given more holes to the semiconductor, that means it will become more p type in the semiconductor. Okay. If it has become more p type in the semiconductor, the Fermi level will move and the surface will move closer to the valence band. More p type means Fermi level will be closer. So, here it will be bending like that. You will have an accumulation layer. Fermi level will be flat, but this will bend. If Fermi level and valence electrons are closer together, it is not the Fermi level it bends, it is the valence electron valence band which moves up. Okay. So, you will have accumulation layer, that you discuss. I just give a hint on that, it will go to accumulation. But please understand that it is not Fermi level which bends, it is the conduction band and valence band which bends. If the valence band bends more close to the Fermi level, it is accumulation. It moves away from the Fermi level, that is depletion in the p type material. Okay. Now, get down to the, I think I have taken quite a bit of time on this particular thing, but in long run you will see it is worthwhile to analyze any situation. So, now I take a situation where I apply voltage. This particular case that I discussed was Fermi, there was no oxide, there was no voltage applied. Now, when I oxidize it, then many of those interface states will be reduced, the surface states will be reduced. Now, when you are, but still some surface states will be there depending upon whether it is thermal oxide, high K dielectric. Now, when I apply voltage plus here, it is getting shared between the oxide and silicon, even when there is no interface state. So, V oxide, you can see now electric field is in the direction from the surface metal to the interior. So, wherever there is plus to minus, if you go plus to minus, the energy band diagram will be like that, because it is difficult for electrons to move to the minus direction. So, you can see the energy band diagram bends up, there is voltage drop in the oxide. You will see quietly in textbooks they will put the diagram here going up like that, implying there is voltage drop across the oxide in that direction. And semiconductor here also bent like this, because plus on the left hand side, plus on the left hand side, plus minus V oxide and then plus minus V silicon. And what is V silicon? Which are calling V silicon, it is history, physics people always called it as psi. We call it as V silicon, drop in silicon. So, they call it a psi of S. Surface potential is nothing but the potential of surface with respect to the neutral region. Okay. So, we have this diagram. Now, you can see the EF in the bulk interior here, neutral region here is decided by the doping, p type material doped. How much doping, that decides this distance. Now, on the surface, the distance between the EF and the valence band edge is more than this one, because it has got depleted. When you say depleted, you can a very casual way of telling is it is less p type, because the depletion is not abrupt, it becomes less and less holes are present, very few holes are present here. So, less p type. So, the distance between the Fermi level and this increases, but the neutral level location is always fixed with respect to valence band edge. Silicon, this is Eg by 3. So, how much charge in this interface state density is present depends upon how much is the distance between E f and E naught is. How much is the distance between these two, it depends upon how much is this E f and how much is this psi of s, total thing. Okay. See, I have here only the E f minus E v. Now, here E f minus E v will include the psi of s and that E naught, that distance. Okay. So, the charge here will be, how much will be the charge here? Will it be negative or positive? Because these is the neutral level. I hope I have not confused you, that is there is a band bending and E naught is below the Fermi level. So, these levels which are above E naught and within that Fermi level are acceptors, they are occupied, there will be negative charge. And what will be charge in the depletion layer? That is negative, because p type depleted negative. So, there will be negative charge here, there will be negative charge in this surface, both are negative. If there were no interface state density, all the charge would have been in the depletion layer. Now, part of it goes into this, is occupied by this. Okay. So, whatever charge in the gate oxide is present is shared by this interface state, that is q dit. A dit is defined as number of states per centimeter square per electron volt. I hope you know about that. I did not mention about that. DIT implies how many states are there, number per centimeter square per electron volt. So, DIT, if it is uniform throughout this distance, E f minus E v is the energy. Per electron volt there are DIT number per centimeter square, and energy gap is difference between the two is E f minus E v. So, if you, I do not know whether I pointed out there, it is left off, but here DIT number into number of levels gives you total number of charges occupied, q gives me the charge. So, q dit into the difference, that gives me the charge. Okay. Now, that is not equal to depletion layer charge, because this charge, negative charge, corresponding plus charge is here on the gate oxide, and there are depletion layer charges which corresponds to this band bending, corresponding to how much is the depletion layer width, q n a into depletion layer width, that is the number of charges per centimeter square in the depletion layer. Okay. All that you know is that the charge here decided by the DIT and the gap between the two, they are negative, and there is charge in the depletion layer. Now, if the gate voltage is changed by delta V g, that delta V g will be shared between the oxide and also psi of x. Okay. That diagram I have drawn here. I have increased that V g by delta V g. So, due to that, there will be delta V oxide, additional voltage drop, delta psi of s. Silicon voltage drop changes by delta V silicon or delta psi of s. Fermi level does not change, but this band bending which was originally solid slightly gets bent more by amount equal to delta psi of s, corresponding to extra drop across the silicon. Conduction band bends down, valence band bends down by additional delta psi of s. Okay. Now, watch very carefully, Fermi level has not shifted, that remains with respect to neutral position same, it is flat, but the neutral level what was here has shifted down by an amount equal to how much this conduction band has moved down. Both conduction band and valence band move together like that. it has deflected by an amount equal to delta psi of s. So, if that has deflected by delta psi of s, the E naught moves by an amount equal to delta psi of s, because E naught is always defined with respect to the valence band edge or conduction band edge, both are same. In the sense, if I in order to avoid confusion, I will say E naught in the case of silicon is 1/3 of E g. So, earlier with respect to valence band, it was here 1/3 E g above that. Now, the band bending, the valence band has moved down by delta psi of s. That means, this level has moved from here to here by an amount equal to delta psi of s, because when the valence band edge has moved by delta psi of s, this level also would have moved down by delta psi of s, because it is written with respect to valence band edge. So, if this has moved with respect to this by delta psi of s, what happens to the charge on the surface? Originally, but the Fermi level has not moved, because that is fixed with respect to the bulk itself. So, there will be additional charge coming because this neutral level has moved down, further down, okay, with respect to the Fermi level, and how much it has moved is delta psi of s. So, what is the charge now, extra charge coming from the interface state density? Q dit, number of levels, multiplied by this shift in that extra charges coming out because due to this shift. So, you will have extra charges coming from the interface density equal to Q dit into delta psi of s. And because the delta psi of s is an additional drop in silicon, depletion layer width would have moved by an amount equal to corresponding amount. So, there will be additional charge in the depletion layer width. So, there are two things happening, because delta q in the gate you have increased, delta q in the interface state density has increased by this amount, Q dit into the shift in this position delta psi of s, okay, and the charge here is shifted by whatever original charge was there by delta q d. Now, let us see. I can define a capacitance corresponding to this. Always you remember delta q by delta v is the capacitance, and delta v is the voltage which changes. So, here the voltage changes is the psi of s. So, when psi of s changes by delta psi of s, the charge changes by delta q I d, which is given by q dit into delta psi of s. So, you can think of it as a capacitance in the equivalent circuit as C I t, which is delta q I t by delta psi of s, which is q dit. It is a constant because we have assumed that the q dit is same everywhere across the band gap. So, you can write C I t, which I think Professor Navkant has already pointed out in some in a different manner, maybe is delta q I t by delta psi of s. Okay. Now, what will happen? Originally, interface state density was equal to 0. We found out the subthreshold slope s equal to n b t log 10, and n was equal to 1 plus C d by C oxide. Now, when you change delta V g, the charge change was only across the C d because of the widening of depletion layer. But now, because of this change in the potential here, not only the charge in the depletion layer changes, charge in the interface state density also changes. That gives rise to an additional capacitance which you put across this. Okay. So, delta B g s by delta psi of s. Now, instead of 1 plus C d by C oxide, you have got 1 plus that effective capacitance, which is sum of C d plus C I t. Okay. So, you have got subthreshold slope now given by 1 plus 60 millivolts into n, that is 1 plus C d by C I t by C oxide. So, what I am trying to point out here is, okay, I did not want that to come there. What we are trying to point out here is interface state density will increase the subthreshold slope. If you go back and see, when you say subthreshold slope, this is the one 60 millivolts per decade. That is, this will be 60 millivolts when the current changes by 1 decade. That is, if n is equal to 1, ideal case. Now, if there is no interface state density, it may not be 50 millivolts, it may be 70 millivolts. But if there is additional interface state density, you will have additional capacitance CIT, that will not be 70 millivolts, it may be 80 millivolts, 90 millivolts, 100, 120, depending upon how much is your CIT. How much is your CIT depends upon the DIT, and DIT depends upon the quality of the oxide. In the case of thermal oxide, the DIT can be very low. People boast of even as low as about close to 10 to the power 10 per centimeter square per electron volt. Okay. But in the case of high K dielectric, it can go 10 to the power 11, 10 to the power 12, unless you use additional passivation techniques. This, please remember that this will be a very important parameter when you go to non-classical, non-silicon MOSFET FETs. Okay. Now, quickly I run through some of the things before I go into some more details. This has been done thoroughly by Professor Navkanth, that is short channel effects. I have only one slide which just completed for the sake of completion. When the channel length becomes small, you can see the depletion layer of the drain region can encroach into the channel in the conventional structure. So, the width of the depletion layer depends upon how much is the total voltage across the drain is. Total voltage is VVI plus applied voltage. I call it as VD. That is equal to QNA W squared by base. This is a standard formula. So, depending upon voltage, you have got depletion layer width. For example, if I have 1 volt total voltage, then doping is 10 to the power 15 per centimeter square. To give an idea, depletion layer width will be 1 microns. So, if I have a channel length of 1 micrometers, the whole channel will be depleted of carriers, which would mean that the entire channel is dominated by the effect of drain and the gate has no control. Okay. So, you want to make it, you increase the doping concentration. To do that, that is why you go to 10 to the power 16, 10 to the power 17, but you know that has other repercussions like reduced mobility and increased threshold voltage. So, you reduce the gate oxide thickness, all those things are there. Now, so that is, if the channel length is 0.1 micron, even if you go to higher doping concentrations, it can deplete all the way, or at least partially. Therefore, I will not get into that discussion. Due to that charge being taken care of by the drain, you will be able to invert the channel with lower gate voltage. That is, the threshold voltage will be lower. That is one of the short channel effects, which I am not getting down for detailed discussion. So, one is punch through, depletion is reaching. Other one is because of the depletion layer occupying the channel here, this charge does not belong to the gate, but to the drain. Therefore, you can invert the channel with lower gate voltage, that is the threshold voltage gets reduced. That is another short channel effect. Okay. Both the things can be reduced by increasing the doping of the substrate. Now, I just wanted to bring in this, the other effect, drain induced barrier lowering. This also has been discussed. I am just drawing what happens here in the subthreshold region. In the subthreshold region, there is no drop across the channel, because the carrier there is no drift current. So, potentially if you see VBI, no drop, VBI. When you apply voltage to the gate below threshold, what happens to the barrier height? It gets reduced, because plus voltage apply, plus minus, plus minus. So, this gets forward biased. So, VBI gets reduced. If the depletion layer width is only here, the first curve here, you will have a reduced barrier height from VBI by psi of s, flat there and going like this. So, this barrier height reduction is completely controlled by the gate. Now, if the depletion layer occupies a good portion of the channel, okay, shorter channel, instead of saying shorter channel, I will say lower doping. This is the depletion layer with encroaching. See, this is the edge of the depletion layer here. The depletion layer edge is here. If you increase the voltage, if I increase the voltage, it is here. If I increase further, if it is reaching very close to the source end, it merges, it will reduce it, the barrier height here completely. So, what was getting reduced by psi of s by VGS gate voltage, now will be a combined effect of the gate voltage and also drain voltage, which would mean the reduction in this barrier height, which gives rise to your current, is controlled by gate and also the drain. Okay. So, the gate loses, it does not have complete control over this reduction, part of it is taken care of by the drain region. So, if that means, if I change the gate voltage now, it supposing let us say it was changing by 60 millivolts per decade, okay. It was changing by 0.1 volt, it was changing. When I change the gate voltage now by 0.15 volts, the psi s will not change by 0.15 volts, because part of the change takes by drain. So, because of the combined effect, gate will not be, if you reduce the gate voltage, okay, from the threshold voltage, if your gate has got a good control, it comes down by 60 millivolts per decade in ideal case. But because of short channel effect, threshold voltage has got reduced, that is why I have drawn it here. Gate has lost control, because the drain also controls that barrier reduction. So, the reduction in the current is not as much as you get in this case. So, the subthreshold slope will not be 60 millivolts, it will be worse than that. If it were earlier, let us say 90 millivolts per decade, in the short channel it may be 100 millivolts per decade or 120 millivolts per decade, depending upon how much is the encroachment. So, these are overcome by this encroachment can be practically reduced in present day devices by providing a lightly doped region in the N plus region called extended drain region. So, this is not so important, but I just pointed out this for continuity. Now, for continuity I pointed it out. Now, the last one that I wanted to say here is this sum up short channel effects. I know that I am redoing stating what was done earlier. You need to increase substrate doping concentration to reduce the short channel effects. That results in carrier mobility degradation and increase in threshold voltage. To reduce, you have to reduce the oxide thickness to overcome this effect. But this of course leads to gate leakage current when you go to nanometer level. But to overcome that, we have discussed already that high K dielectric is used. But when you use high K dielectric, you know that there are a lot of interface state density effects. So, you encounter those effects. So, you need to have some passivation techniques also done there. Now, when you also use high K dielectric, you must ensure that this energy between the conduction band of silicon and the conduction band of the dielectric must be high enough. If it is not high enough, the electrons which are here can climb up here, get into the dielectric. Okay. In the case of silicon, they do get into that region when you go to large voltages, large electric fields. But today you do not have to worry much about that in the case of silicon, because you talk of low voltages. So, fields are not that high, or your velocity energies are not that high. Energy is equivalent to V, V small energies are not that high. So, but still if this height is not sufficiently large, you can have electrons injected into this dielectric. You can consider them as hot electrons, and once they are injected into the dielectric, they can act as additional traps in the dielectric that can change threshold voltage, that can give rise to reliability problems. So, What you have to take care when you go for dielectric materials is not only that it has could have good band gap, it must also have this gap between the conduction band and that is the chi. This depends on how much is the distance between this conduction band of the dielectric and let us say the 0 level. Let us say 0 level is there, between that and this, how much is the gap? How much is the gap between the conduction band and the 0 level? Silicon, it is 4.05 electron volts, and you, in the case of oxide, this gap is 3.3 electron volts. This gap is 4.05, that is E 0 level, and this gap is 4.05 minus 3.3 electron volts. So, this gap is more. Supposing this is also 4.05, this is 4.05, the band gap may be large, but the inverted electrons can get passed through the oxide. There will be gate current, and or they can get trapped in the oxide. These are some of the things one has to remember when one gets into, when one thinks of going to high K dielectrics. Okay. Now, the effects of short channel. Oh, I just come to very close to end of the thing. There is there are different effects coming up. How many minutes? About 7 minutes. Okay, I will just at least few things I will do now. So, this is the one which I want to discuss in more detail. I need one more session on this. So, but I will just get into at least what is this meaning. You remember in the beginning itself we said the first order theory of MOSFET, we assumed that Ohm's law holds good. When we said Ohm's law holds good, we said V is equal to I into R, which again means that the velocity of carriers is proportional to electric field. Velocity is equal to mobility into electric field. Now, if you take a look at the silicon MOSFET or any other MOSFET, for example, that is the way the charge distribution is. Charge is more here, charge is less there because of voltage drop across the channel. And because of that, because of this change in charge, you also remember you wrote the current is I d is equal to Q into V. Q is charge per centimeter square. When you move from the source to the drain, we took Q is varying, we took velocity is equal to mu into E, electric field. That way you derived the equation. Now, you take a look at this. When you move from here to here, Q is falling, what would happen to the velocity? Current is Q charge into Q into Q n into V. N is decreasing, velocity must increase. So, if I am saying V is equal to mobility into electric field, what happens to the electric field? Mobility is constant if I take, electric field is increasing. Okay. So, what you say is, as I move from here to here, evidently the electric field is not constant, electric field is increasing. Okay. Now, what will be the electric field? If I take an average electric field, you can say that what is the drop across the channel? When it is opened here, the channel potential is Vgs minus V threshold, V is the V threshold. So, that divided by channel length is the electric field. So, average field depends upon how much is the voltage drop across the channel, average voltage drop. Okay. So, average voltage drop is always channel drop, that is Vg minus V threshold we saw after saturation. So, that is average field. Now, let us see what happens to as we keep on reducing the channel length for a given threshold voltage. Average electric field actually for a given threshold voltage, let us say this is not changing, for shorter the channel length, more is the electric field, average electric field. Even at this end, if you take the average electric field, everywhere it will be high. Even though it is varying, there will be high electric field. So, what happens when the electric field is high? Can you take mobility is equal to or mobility is constant, can we take? What is velocity? The velocity is actually force divided by mass, that is acceleration, into time. Okay? So, acceleration into time. So, as the electron is accelerated, it experiences collisions, that is, it gets scattered. So, at that, when the collision takes place, it comes back to rest. It accelerates, collides, it accelerates, collides. So, the velocity, the average velocity, you can put it as the force, that is the acceleration, that is force divided by mass, the force q into E, average field between collisions divided by mass into the time of collision. So, that is called mobility into electric field. Now, when the electric field goes up, acceleration goes up. So, time between the collisions decreases. So, if the time between the collisions decreases, okay, q tau by m decreases. So, when you write mu here, q tau by m is the mobility. Okay. So, you have got the mobility which you assumed constant is no longer constant, it decreases as the electric field increases because the tau falls. Or to put it in simple terms, if I plot velocity versus electric field, okay, the velocity, because of reduction in the collision time for an average electric field, the velocity does not increase linearly with the electric field, it goes on increasing like that, then saturates. Okay. So, I will not go beyond that. This saturation, why it comes, we will just discuss very briefly next time. So, today I will stop that ultimate velocity of the electrons is limited by the saturation velocity. Okay. So, that velocity is about 10 to the power of 7 per centimeter per second for silicon, and also even for gallium arsenide and for many materials. And the electric field at which it saturates is about 30 kilovolts per centimeter. So, with that I think we will close down today. We will discuss more details in my next presentation, all these aspects starting from this slide. Okay. Thank you.